Hello. In this session, we will design a 4-bar Grashofian linkage, and then we will simulate the linkage to study its inversions. First inversion, that is crank rocker, is obtained when we fix the link adjacent to the shortest link, that is this link or this link. Next inversion of double crank is obtained when we fix the shortest link, okay? This one, which is having length of 40 millimeters, and last inversion, that is double rocker, is obtained when we fix the coupler link, okay? Link opposite to the shortest link, which is having length of 100 millimeters. So first of all, we will design this linkage. We will call this as link number 1, whose length is 80 millimeters, and this as link number 2, this as 3, and this as link number 4. So first of all, let us design this link having length of 80 millimeters. So here we go to the part design. We'll name the part as link 1. Select the sketch plane, and using the profile toolbar, we'll create link number 1. So let us align this axis with horizontal axis using coincidence constraint. Then we'll make center of these two arcs symmetrical about this vertical axis using symmetry constraint. We'll dimension this radius as 5 millimeters and center to center distance for link number 1 is 80 millimeters. So we'll change the value to 80. Now we'll place two circles having diameter of 5 millimeters at the center of the circular arch. We'll add the material using the pad tool on both the sides of sketch plane by selecting mirror extend, 2.5 millimeter on each side of sketch plane. Now let us change the color of this link for okay. Let us save this file. By the name of link number 1. Now we'll design link number 2. Link number 2 is having length of 40 millimeters. So select the sketch plane. Now we'll make this arc center symmetrical about the vertical axis using symmetry constraint. Then we will keep this radius as 5 millimeters and distance between these two centers is 40. Now again we'll place two circles having diameter of 5 millimeters at the center of these two circular arcs using concentricity constraint. Now let us add the material using pad tool on both sides of sketch plane using mirror extend by an amount of 2.5 millimeters. Let's go to the property and we'll change the color for this link as change the color to green. Let us save this file in the same folder in which we have saved link number 1 by the name of link number 2. The next we'll design link number 3. And length of link number 3 is 120 millimeters. Select the sketch plane using sketcher tool. Again make centers of these two circular arcs symmetrical about the vertical axis using symmetry constraint. Change this radius value to 5 millimeters and center to center distance for link number 3 is 120. Again we will add two circles having diameter of 5 millimeters at the center of these two circular arcs. We'll add the material using pad tool on both sides of the sketch plane using mirror extend by amount of 2.5 millimeters. Go to the properties. Let us change the color of link number 3 to the blue. We'll save this in the same folder in which we have saved link number 1 and link number 2. Next we go for designing link number 4. Length of link number 4 is 100 millimeters. So select the sketch plane, make use of profile tool, then make the centers of these two circular arcs symmetrical about the vertical axis using symmetry constraint. Change the value of diameter to 5 and center to center distance of link number 4 is 100 millimeters. Now let us add two circles having diameter of 5 millimeters at the centers of the circular arcs. Now add the material using pad tool on both sides of the sketch plane by amount of 2.5. Go to the properties and let us change the color of this link. We will save this file in the same folder in which we have saved link number 1, 2 and 3. Now let us do the assembly. So we'll enter the assembly module. Select the name of assembly. Let us change this name as 4 bar linkage. Click on 4 bar linkage. Select existing component tool from product structure tools toolbar. Browse to the folder in which we have saved all the 4 files. So we'll first of all insert link number 1. Apply the constraint of fix. We check the degrees of freedom for this link number 1. There is no degree of freedom, so we have fixed this link in all the directions. Now we will insert link number 2. Select the manipulation toolbar to position the links. Then we'll apply the constraint of coincidence to these two axes and constraint of contact to these two surfaces. Let us update the constraints. We'll use the manipulation toolbar. Okay. Now we will insert link number 4 first. Apply the constraint of coincidence to both this axis and constraint of contact. Okay, and now we'll update these constraints. Okay. Now we will insert link number 3. Use the manipulation toolbar to position these links. Coincidence to these two axes and contact these two surfaces and update the constraint. Let us use manipulation toolbar to position this link. Coincidence to both these axes, and let us update this constraint. Now we will check the degrees of freedom of all these links. First one is fixed, we have checked that. Now degrees of freedom of link number 2, there is 1 degree of freedom for link number 2, that is of rotation about x-axis. This one. Link number 4, rotation about x-axis, 1 degree of freedom. And link number 3, rotation about x-axis, like this. So we are correct. Now let us hide the constraint symbols and we will hide all the planes. Planes of link number 2, then planes of link number 1 and 2, then planes of link number 4, and link number 3. Okay. Now we completed the assembly. Now let us save this file in the same folder. Now we will simulate this mechanism. Go to the digital mock-up DMU kinematics. Now we'll create the revolved pairs between all these links. Okay. So here, use the tool revolved join from DMU kinematics toolbar. So mechanism 1. This one and this axis, this plane, this plane. So this is joint number 1. Next revolved joint, this one, this axis, this surface, this surface. Okay. We have created two revolved joints with these fixed links. There's two axes, this plane, this plane. Okay, so 3 revolved joints. Now last one, axis of this link, axis of this link, this plane which is in contact with this plane. Okay, now we have created 4 revolved joints. Let us check. First revolved joint is here, second revolved joint is here, third one is here, and fourth one is here. Now we will produce the command of angle driven for joint number 2. We will hide all these constant symbols. Now let us add the simulation. First of all, we will do the simulation for this first inversion, which is crank rocker, which is obtained by fixing the link adjacent to the shortest link. So this is our shortest link. Now we'll fix this link to produce the crank rocker mechanism. Okay, so fix this link. Okay, go to the simulation tool. So first of all, we will change the values of this command from 0 to 360 degrees. Okay, the simulation mechanism 1, insert. This is the velocity of the moving links. These are the steps. So let us play. So this green link, which is smallest link, is acting as crank, and this link number 4 is acting as rocker. Okay, and this is the fixed link, which is adjacent to the shortest link. And this is the first inversion crank rocker mechanism. We'll create the replay, name it as crank rocker. Velocity of the moving links is 0.01. So you can check that replay from model tree. Now we will change the fixed link. Now let us fix the shortest link and check the simulation. You can see the shortest link, which is shown in green color, is fixed, and the links attached to the shortest link are acting as double crank. Now let us create the replay of this by the name of crank crank. Let us check. It's okay. Now again we will change the fixed link to get the third inversion, which is obtained by fixing the coupler link. So fix the link opposite to the shortest link. Now let's check the simulation. Now this link is fixed, which is opposite to the shortest link. The link adjacent to the shortest links will act as rockers. They will oscillate about the pivots of fixed link. This one is oscillating, blue color link, and this one is oscillating, brown color link. We'll produce the replay of this as rocker rocker. Now let us check the angle of oscillation of the rocking links. For that, use trace command. Now we will do this for crank rocker mechanism, and elements to trace. We will trace when we fix this link, we get crank rocker mechanism. Green link is acting as a crank, and this link will act as a rocker. So we'll trace the displacement of edge of this rocker. So this is the path of motion of the rocker while the crank executes 360 degrees of rotation. We can measure the angle of oscillation by using this tool, measure between. I am selecting approximately, but you have to select the first line and then the last line. So the angle of oscillation approximately 72.231 degrees.